Alright, before I start, let's have a couple of announcements. The first one is that I have to take off right after class today, so if you come talk to me after class, normally that's not a problem, but today I'm going to have to snub you and just walk out of here, so come find me some other time because I do have to leave today. Then the other announcement is a week from today, which is April 11th, the first and only time this year that we won't have class because I'll be traveling for business. So what don't sound too happy. So what I'm going to do is, to maintain continuity and not fall behind, I'm going to record a lecture on my own, which I'll be posting on YouTube, so hopefully that's an acceptable alternative. I thought about also getting a sub, but then I would have wanted to do the video anyway for continuity, so I'll just leave it up to you guys to learn that stuff by watching the video on your own, which will be not too different than what we have in class. Okay, I'll send email reminders about that. So that's coming up next week. Alright, so let's get into what we're going to do today. So last time we talked about all of these individual gas laws, which were derived by looking at the relationship between the volume of a gas and the other parameters that are associated with that gas, namely the temperature, the pressure, and the number of moles. So we saw that there was three individual relationships, and you should be at least a little bit familiar with these, at least the names of them, just from a historical standpoint, are important. So we have Boyle's law, which is that the volume was inversely proportional to pressure. We had Charles's law, which was the relationship between volume and temperature, which are directly related. And then Avogadro's, which is the relationship between volume and number of moles, also directly related to each other. So volume is proportional to all three of these things. It's proportional to 1 over the pressure, to the temperature, and to the number of moles. And what we have, a trick we've already used once or twice in this course, and we used it a little bit when we were talking about the equation for heat, mc delta T. If you have a parameter that's proportional to three things separately, it's also going to be proportional to the product of those three things. So we can combine these three into one equation by taking the product of everything that volume is proportional to. So that means volume is going to be proportional to 1 over the pressure times the temperature times the number of moles. It's proportional to all three of those things multiplied together. And then if we move everything so we don't have any fractions anymore, pressure times volume is proportional to the number of moles times the temperature. And then this is starting to look familiar to us because now we know that if we have a proportionality and we want to change it to an equality, so we want to replace this proportional sign with an equal sign, we just have to put a constant on one side of the equation. And we're going to, for reasons that I won't get into, we're going to put the constant on the right side of the equation, and we're going to write this as PV equals nRT, where R is the constant that we're putting in to make these equal to each other. All right? And because these four variables, pressure, volume, number of moles, and temperature, because they tell you everything that you want to know about an ideal gas, these are referred to as an equation of state. And the importance of this is now when we include all four of these parameters in the same equation, we have one value for the universal gas constant R, and it's going to be, you'll find it on your periodic table, it's 0.0821 liter atmospheres per k mole. And it's referred to as the universal gas constant. Alright, so this here, PV equals nRT, is the equation that dictates all of the relationships between these variables in a sample of a gas. And what I want to hope to convince you by doing some problems today is, even though we have these three separate relationships that we derived last time, if you know the ideal gas equation, that's the only one you actually have to know. You can do any sort of problem involving gases where you're looking at relationships between initial and final conditions, where you're changing one or more of these variables. You can do any sort of problem like that just by starting with the ideal gas equation. You don't need the separate ones that we derived last time. Okay, so that's what we're going to go into today, is just doing a bunch of, to start with, we're going to do a bunch of example problems involving the ideal gas equation, PV equals nRT. You should also note on your periodic table there's two values of R which have different units. So one of them is in joules per kmol. That's one that you'll use later on, maybe once in this course, but definitely a lot in chemistry too. You'll see the other value of R, which has other context that it's important in. All right, but let's get into the problems. So there are basically two types of problems we could ask you to do with ideal gases, and using the ideal gas equation specifically. So one of them is we give you 3 of the 4 variables: pressure, volume, number of moles, temperature. We give you 3 of those 4, and you have to solve for the other one. So this is just simply rearranging the ideal gas equation and finding whatever whatever parameter you don't have. So in this first example here, we have a sample of neon gas with a volume of 2503 milliliters, and we have a pressure of 551 torr, and the amount is 0.1 mole, as you say. What is the temperature of the gas? So in this situation, we're not talking about changing any of these variables. We're not talking about increasing the pressure or decreasing the volume or anything. We're not talking about any sort of change. So we just want to use the ideal gas equation and solve for whatever our unknown is. So here we're solving for temperature. So we're just going to rearrange this equation and say that temperature is equal to pressure times volume divided by N times R. And one thing that's important about this is if we're going to use the value of R when we're doing a calculation, if that shows up in whatever we're doing, we have to make sure we are careful about units. Remember that R is 0.0821 liter atmospheres per kmol. Come on. No. Alright, so kmol, sorry. And what this means is that your volume when you're using R has to be in liters, your pressure has to be in atmospheres. For any type of ideal gas problem where you're using absolute temperature, temperature has to be in Kelvin. That's no exception. And then of course the amount of substance is in moles, which is the typical unit for that. But especially pressure and volume and temperature, we need to make sure they're in the right units for us. So our pressure here is 551 torr. That's not the unit of pressure that R is in terms of, so we have to do that conversion first. So a lot of times ideal gas problems will frequently involve some unit conversions as part of them. So if we give you the pressure in torr, remember that the relationship we learned last time is that 1 atmosphere is 760 torr. So we just divide the two to convert. So our pressure in atmospheres would be 0.725. And then our volume needs to be in liters. We're giving you a volume in milliliters, 2503, so we have to then convert that into liters. So it's going to be 2.503 liters. And our temperature is what we're solving for. That's going to be in Kelvin once we insert the units correctly. All right, so we put everything in that we have now. Our pressure in atmospheres is 0.725. Volume in liters is 2.503. And then N is 0.1 mole. And then R is 0.0821 liter atmospheres per kmol. And we see that all the rest of the units cancel out. Liters, atmospheres, mole cancel out. We have 1 over Kelvin, or Kelvin is finally, 1 over Kelvin, which gives us the absolute temperature. So this comes out to 221 Kelvin. If we asked for you to report it in degrees Celsius, you would subtract 273 from that to get minus 52 degrees Celsius. So again, didn't specify a unit here, but either of these would be correct. 221 Kelvin, but what you initially solve for will always be in Kelvin when you're using the ideal gas equation. So this equation or anything that's derived from it has to be in terms of absolute temperature, which must mean you're using the Kelvin unit and not anything else. Okay, questions on how we use that to solve problems of this type? Now, the more common scenario for you is going to be using the ideal gas equation to derive relationships between these where you're changing one or the other. So we saw last time that there were 3 relationships that we got from Boyle's law, Charles' law, and Avogadro's law. We can derive any of those as well as other ones by using the ideal gas equation. That's what we do here. So we have a balloon with a volume of 255 milliliters and a pressure of 912 torr, and the temperature is 25 degrees Celsius. And then we allow it to rise up to the atmosphere where the temperature and pressure are minus 23 degrees Celsius and the pressure is dropped to 2.28 torr. What is the volume of the balloon under these conditions? So we did a problem like this last time where just the pressure was changing, but now we're looking at a situation where pressure and temperature are changing. So the pressure is going from 912 torr to 2.28. The temperature is going from 25 Celsius to minus 23 Celsius. And so both of those are changing. How does that affect the volume? So we need to derive a new relationship that involves these three. And so what we always do is we start with PV equals nRT. And we want to identify which variables in this equation are constant in this problem, which ones are not changing. So in this particular situation, we're asked about the volume, so that's one that's going to be changing. We see that the pressure, as we said, is changing and the temperature is changing. However, we're not told anything about the number of moles, so if we're not told anything about it and we know that this is a closed container, it's a balloon, which, assuming our balloon doesn't leak or pop, that means the number of moles will be constant. We have a closed container of gas, so we're not changing the amount of gas that's present during this experiment. So the number of moles is constant. It's a closed container. So anytime you see the word closed container, or you can presume that it is a closed container from the problem, you know that the number of moles of gas is not changing. So that's one of our constants in this situation. And then the other thing that's always constant is going to be the ideal gas constant R. So when we're setting up problems like this where we want to derive a new relationship, we move everything that's constant over to one side of the equation and everything that's not constant over to the other side. So we're going to do pressure and volume and temperature are changing, so we're going to move temperature over and then rewrite the ideal gas equation like this. And then this is all going to be equal to a constant because N and R are both constant. So whenever we have this situation where we have two or more variables, some relationship between them equal to a constant, we can set the initial and the final conditions equal to each other. So the ones that are changing are pressure, volume, and temperature, which means that pressure 1, so P1 V1 over T1 must equal P2 V2 over T2. So this is how we rearrange the ideal gas equation, and whenever we have two or more variables changing, we isolate the ones that are changing and we derive a new equation for this. So we could also derive the equations we saw last time with just two variables. This one has three, and we can also get that relationship just starting with the ideal gas equation. And so this is what we're going to use. We're going to use this equation, and we're solving for the final volume, which is V2, which is going to be then P1 V1 T2 over P2 T1. So we just rearrange this equation to solve for the final volume V2, which is what we're interested in, and now we just have to start plugging things in. Now the other nice thing about doing it this way is that because we don't have the universal gas constant R in this equation anymore, we have a little bit more flexibility with units. The one that still has to always be the case is temperature has to be in Kelvin, but if we have a ratio of two pressures, P1 over P2, we can use whatever units we want as long as they're the same, because those units will divide out. And same with, in this case, the temperatures, though, they have to be in Kelvin, and then the volume can be whatever unit we want it to be as well, because we don't have the universal gas constant R as part of this calculation anymore. So P1 is 912 torr. The initial volume was 255 milliliters. And then T2 is going to be in the numerator, so that's going to be our final temperature. We need that to be in Kelvin, so our T2 is going to be minus 23 degrees Celsius plus 273 to get it into Kelvin, so that's 250 Kelvin. And then in the denominator we have P2 and T1, so the final pressure is 2.28 torr. So the units torr divide out, so they don't have to necessarily be atmospheres in this case. And then the final temperature, though, is 225, or sorry, that's the initial temperature, 25, which is 298 Kelvin, plus 273 to get that. And so what this comes out to, so the units for temperature cancel out, but don't forget they always have to be in Kelvin, because Kelvin is the only temperature unit where the temperatures are related on an absolute scale. Because in Celsius you're shifting the scale by 273, so the relative ratios of the two temperatures wouldn't be the same on the Celsius scale. So what this comes out to is 85,570 milliliters, or about 85.6 liters. This would have to be the world's strongest balloon to expand from 255 milliliters to 85 liters without popping, but this is just a thought process. It's just on paper sort of thing. So that's what we would calculate for the final volume. So to expand by quite a bit as we go to the lower temperature and especially the lower pressure that you have in the upper atmosphere. Okay, so that's one example of how we can use the ideal gas equation to derive new relationships. And again, when you have changing conditions, figure out how those perturbations affect one of the other variables. Okay? Let's do a couple more, I think. I forget how many I put in here. All right, so this one here we have, I think I got things out of order. Here we go. All right, so we have a gas cylinder that has a fixed volume. So fixed volume tells us that volume is constant. And it's filled with 239 moles of hydrogen, which gives a pressure reading of 136 atmosphere. 176 moles are removed from the cylinder. So what is the new pressure reading? All right, so in this situation we have, again, starting with PV equals nRT. We're looking here for a relationship between pressure and number of moles, because the number of moles is changing, and then we're asking what is the new pressure when we remove gas. So what we're assuming here is that the temperature, the volume, and of course the universal gas constant are all constant. All right, we didn't say anything about the temperature changing, so in the absence of any of that information, you would assume that it's constant. We're not asking about temperature. As we said, the volume is fixed, so you're not going to change the volume. And so really the only two things that are changing are pressure and number of moles. So we move those over to the same side, and we move everything that's constant over to the other side. You could have also written it as n divided by p is equal to v over rt. As long as you correctly rearrange the equation, you can do it in any way. And this is all going to be equal to a constant. So we move the variables that are changing over to the left side, over to one side, and then what we're going to say is we're going to take the initial conditions, P1 over N1, this ratio of pressure divided by number of moles has to equal the final ratio, P2 over N2. And what we're solving for here is the final pressure, P2, which is going to be P1 times N2 over N1. So we just solve for what we're asked for, which is the final pressure, the new pressure reading, and we just start plugging in the numbers. Now we know that our initial pressure is 136 atmospheres, so we can plug that in. Our initial number of moles down here, N1, we're told directly is 239. We have to be a little bit careful in this problem with N2. So N2 is not the number of moles we removed, it's the number of moles that are left at the end. Okay, so whenever we're talking about the ideal gas equation, if we're talking about the term N, which is the number of moles, we're talking about the number of moles of the gas that we have, not the number of moles that we've removed or added. So this final number of moles, N2, is the amount we started with, 239. We subtract the amount we took out, which is 176. Which is then 63 moles left. So that's the number of moles of hydrogen that are left at the end after we've removed the amount that we specified. So that's going to be 63 moles there for N2. Moles cancel out, and that gives us a final pressure reading of 36 atmospheres. Okay? So not too surprising, if we remove gas from the cylinder, the pressure goes down. So this is a relationship between pressure and number of moles, which is not one of the gas laws we talked about last time. I don't even think this one has a special name, but it can be also derived from the combined ideal gas equation. All right, so those are just a couple example problems. There's a lot more variations on this theme. Well, let's get into then the next topic. So any questions on those last two before I move on? I don't want to get ahead of myself. All right, so the next topic we're going to talk about, which is also comes straight from the ideal gas equation, is how do we determine the density of a gas. So we said last time that density of a gas they tend to be small compared to liquids and solids especially, and how do we calculate what that is? And there's a relationship that we can get from the ideal gas law. So we start with PV equals nRT. And so again, if you can follow what I'm doing here, you don't necessarily have to memorize the final equation that I'm going to get. We start with PV equals nRT and we just make some substitutions. Now we know from starting in Chapter 5 and continuing through everything else we've been doing in this course since then, we can rewrite number of moles here as the mass divided by the molar mass, where M is the mass in grams, MW, as I'm abbreviating it, is the molar mass. So we can rewrite the ideal gas equation as pressure times volume is equal to mass divided by molar mass times RT. So if we know the mass of the gas, we'd be able to rewrite the ideal gas law in this way. We also know from things we learned a long time ago that density is equal to mass divided by volume. So what we're going to do is we're going to put mass over volume on one side of the equation, everything else on the other side, and what that leaves then is, on the other side, pressure times molar mass divided by RT. So we just multiply both sides of the equation by molar mass, and then we divide by RT to isolate M divided by volume. Okay? So we're just rearranging this equation here to solve for the mass over volume ratio, which is called density, and that gives us this equation. So the density of a gas is dependent on its pressure and its molecular weight and its temperature. Those three things will determine the density of a gas. All right, so the way we use this would be a straightforward example being if we have a sample of ammonia gas and we want to know the density at 500 torr and 37 degrees Celsius. If we're just calculating density, we use this equation. Pressure times molar mass divided by RT. And now we just have to put things in. Now again, in this equation we're using the value of R, the universal gas constant, so we need to make sure that our other terms have the correct units associated with them. So R is, again, liter atmospheres per kmol. So anytime we're using R, we need to have the pressure in atmosphere. So we need to take this 500 torr which is 1 atmosphere per 1760 torr, 0.658 atmospheres. So that's the pressure of the gas in the correct units. We need molar mass for ammonia. We all know how to calculate molar mass. Now it's just the sum of the atomic masses, which is 14.01 for nitrogen, 3 hydrogens, which are 1.01 grams per mole. So the sum of those would be 17.03 grams per mole for NH3. So that's molar mass. And then the last thing we need is the temperature in Kelvin. So 37 Celsius is the temperature we're given. We add 273 to convert it into Kelvin. And that comes out to 310 K. All right, so these are the three terms we need in their correct units. And so we're going to go ahead and put those back into this equation. 0.658 atmospheres, 17.03 grams per mole. R is 0.0821. And then temperature we determined was 310 Kelvin. All right, so paying attention to the units we have here, atmospheres cancel, Kelvin cancels, moles cancel, and we're left with a number 0.440 with the units of grams per liter. So that means under these conditions, I can't write today, well, any day. 0.440 grams per liter. So that's the density. Now we should think about that number for a second. I told you that the density of the gases are low. And you might say, well, that's not too low because water is 1. But remember, water is 1 gram per milliliter. This is 1 gram per liter. So it's over 1,000 times smaller. And this is a reasonable temperature and pressure. You know, close to 1 atmosphere, 37 Celsius is body temperature, so not too hot. And so under these conditions, the density of the gas is pretty, over 1,000 times smaller than what you would have for water. So gases do have low densities. They're typically reported in grams per liter instead of grams per milliliter, and that's the units that come directly out of this equation using the value of R that we have, 0.0821. All right, that's how we calculate the density of a gas. Of course, there are variations on this. We could ask you to calculate molecular weight. So if you want to know, the molecular weight of an unknown gas, we would have you solve for that. You can rearrange this equation in a few different ways, but this is really the only equation we'll have to worry about when we're talking about the density of a sample of gas. All right, so that takes us to our next topic then, which is using the ideal gas law to help us do stoichiometry problems. So everybody's favorite topic, stoichiometry, will not die just yet. So we're going to talk about it a little bit in this chapter as well, and how we use the ideal gas equation in stoichiometry problems. And so let's review then the different ways we have to calculate moles, because what we've been doing in the last 3 chapters now is sort of building up our toolbox, the number of relationships we have involving moles. So the first one we learned, which is the definition of the mole, is that the number of moles, which I'll abbreviate as N to stick with the ideal gas convention, is number of entities divided by Avogadro's number. So if we knew exactly how many molecules or atoms we had, you could divide by Avogadro's number to find number of moles. That's one way we learned back in chapter 5. That's not the most practical way because we don't often go into the lab and count molecules and atoms. But then the other ways that we use, which are much more practical for us, are what we learned in the other one in chapter 5, which is the relationship between mass. We've already used this today. The number of moles is the mass in grams divided by the molar mass, which is grams per mole. So we know this relationship. We've used this one probably the most of all of these. And then the one that came up in chapter 6, the last chapter that we covered before the second exam, is that the number of moles is equal to molarity times volume, where again capital M is molarity, moles per liter of solution. So that's a relationship for moles that we used a lot when we were doing solution stoichiometry and when we were doing titration problems, which is just an application of that. So those are the three we've already learned. And then the one that we have now in this chapter from the ideal gas equation, starting with PV equals nRT, the number of moles is equal to pressure times volume divided by RT. Now, one thing that comes out of this, and I don't have any examples that directly speak to this, but I'm sure I'll go through some on the homework review and probably on the exam review as well. You notice that the number of moles is directly proportional to pressure, and it's also directly proportional to the volume. So all three of these things are directly related: number of moles, pressure, and volume. So if we have a gas phase reaction, let's say we have the formation of water vapor by burning hydrogen. So if we have 2H2 plus O2 all in the gas phase, and they're reacting to make 2H2O, water vapor. So let's say we're doing this reaction. Now the way we learned how to interpret chemical equations in chapter 5 was, this tells us that 2 moles of hydrogen plus 1 mole of oxygen combine and make 2 moles of water. Now of course that's still true, but if we're talking about gases, and we have all of the reactant and product gases at the same set of conditions, we could also read this as 2 atmospheres of hydrogen plus 1 atmosphere of oxygen makes 2 atmospheres of water. Or if we want to do it in terms of volume, if all the gases are at the same pressure, 2 volumes of hydrogen combines with 1 volume of oxygen to make 2 volumes of water. So when we're talking about gas phase reactions, we can use, in some sense, when we're talking about stoichiometric coefficients, we can use number of moles, pressure, and volume almost interchangeably. So there will be some homework problems where it's never going to be necessary to use that relationship, but it can save you a lot of time instead of always having to convert into moles. Now, if you feel safer and more comfortable to do it that way, you can always use the ideal gas equation to convert into number of moles, provided you have the pressure, the volume, and the temperature for all the gases. So we'll keep that in mind. Now, the one that I'm going to go through today doesn't actually require us to use that relationship. I just wanted you to be aware of it. So let's do an example problem, a couple of these anyway, with gas stoichiometry. All right, so let's say we have nitrogen and fluorine, and we're combining them in a 1:3 mole ratio and a total pressure of 1.25 atmospheres, and we're going to form NF3 quantitatively. If the reaction is carried out at constant temperature and volume, what is the final pressure at the end of the reaction? All right, so what we're doing here is we're taking, this is the chemical equation, N2 plus 3F2 going to 2NF3. So what we're changing is the number of moles. So we have PV equals nRT. And during the course of the chemical reaction, the number of moles is changing. So we're telling you that the temperature and the volume are constant, but as we go from reactions to products and do this reaction, on the reaction side we have 4 moles of gas, 1 mole of nitrogen, 3 moles of fluorine, at least that's the ratio of those two. And then on the product side, the ratio, we have only 2 moles of gas. So the two things that are changing are pressure and number of moles. So again, using that same equation we derived before, pressure divided by number of moles is equal to RT over V, which is a constant. And then P1 over N1 equals P2 over N2. Alright, so this is the same relationship we used earlier, except this time we're not adding moles of gas, the same gas, we're actually doing a chemical reaction that's changing the number of moles of gas. So the final pressure would be P1 times the ratio N2 over N1. So our initial pressure was 1.25 atmospheres. And then what we need is the moles N2 over N1. Now if we look at this problem here, we're not telling you exactly how much gas we're using. We're not telling you the masses of the gas. We're not telling you the number of moles directly. So how do we find the ratio N2 over N1? So N2 is going to be the moles of product. That's the amount of gas we have at the end of the reaction. N1 is going to be the moles of reactants that we have. And so what we're looking for is the ratio of N2 over N1, which is the moles of product divided by moles of reactant. And as I said, from the balanced chemical equation, we see that we're forming 2 moles of gas as a product. And then on the reactant side, we have a perfect 1 to 3 mole ratio. So we know that on the reactant side, we have 1 plus 3, which is a total of 4 moles of gas. And something that may be a little bit unclear now, but we'll get to a little bit later today, is when you're talking about the pressure of a sample of gas, if you mix 2 gases together like we would have when we react these two, the total pressure is just determined by the total number of moles of gas, not by the identity of the gases. So we have 4 moles of gas as reactants. And as I said, we don't know the exact amounts of each that we're using, but we know that the ratio will be 2 over 4. Okay? And so that ratio, no matter what scale we're running the reaction at, we're going to form 2 moles of product per 4 mole of reactants that we use. And that gives us then a final pressure of 0.625 atmospheres. So in this reaction, we're decreasing the number of moles of gas present because we're going from 4 moles of reactants to 2 moles of products. And because we're decreasing the number of moles of gas, the pressure also decreases. And this is how you would calculate it. Now that one was maybe a little bit of a strange way to set it up. Any questions before I go to the next one? All right, so the next one is a little bit more involved and I think a little bit more fun. All right, so we have the following reaction, which is carried out at 400 Kelvin. So we're taking pH3 gas, which is called phosphine, reacting it with O2, and we're making solid P2O5, and we're also making water vapor as a byproduct. So we're doing it in the following way. So this is a way that we often do gas phase reactions. We have 2 bulbs of the gas. So the first bulb, which has a volume of 12.5 liters, is filled with 2 atmospheres of pH3. And then the second one here, bulb B, has a volume of 10 liters and has 3 atmospheres of O2. And they are initially closed off by the valve, which I've labeled as C. Okay? So they're initially isolated from each other, the 2 separate gases. So before we allow them to react with each other, let's ask the question, how many moles of each gas are present at the start of the reaction? So we have 2 samples of gas. We know the pressure and the volume. And we also know the temperature, so we can figure out number of moles using ideal gas equation. So for both gases, the number of moles is going to be the pressure times the volume divided by RT for that gas. So we have to do it separately for pH3 and O2 because the 2 gases initially have different pressures and different volumes. So we have to calculate these separately. So for pH3, we have the initial pressure is 2 atmospheres. And here I didn't play any shenanigans with units, so we can just use that directly. And the volume is also in liters, so we can use that directly. 12.5 liters is the volume of the container that gas A resides in. And then we divide that by RT. So 0.0821 liter atmospheres per K mole. And we're telling you here that the temperature of the reaction mixture is 400 Kelvin. So when we calculate the moles of pH3, we get 0.761. So that's how many moles of gas are in this flask that I've labeled A. And then we're also asking you to figure out how many moles of oxygen are in the second one, flask B. So for oxygen, we see that the pressure is 3.00 atmospheres. That's that number there. That's the pressure of the oxygen sample. The volume of bulb B is 10 liters. So that's the volume of that. And then RT is the same. So universal gas constant, of course, doesn't change. And we're doing this all at 1 temperature. So it's going to be 400 Kelvin. And so the number of moles of oxygen is going to be 0.914. Alright, so that's the number of moles of each reactant we have before we allow them to mix with each other. So just like any stoichiometry problem, if we're trying to ask you questions about reactants and products, the first thing we should think about is how many moles of each reactant we have. That's a very common thing we do. So now we know the moles of each reactant. Let's see what the next question asks us. So we open the valve between the two. So this valve that I've labeled as C, we open it up and we allow the two gases to mix together. And as we talked about when we were introducing gases, gases are freely diffusing and they fill all available space. So once we open the valve, we allow the two to mix together, they're going to come together and they're going to fill this entire volume of the whole apparatus. Okay? So the gases are allowed to react. We want to know which gas is a limiting reactant when they're mixed together and allowed to react with each other. So just like we saw before in any other stoichiometry problem, the way that we can determine what the limiting reactant is to calculate what's called a stoichiometric ratio. And so we saw in the last step that the number of moles of pH3 was 0.761. The number of moles of O2 is 0.914. And this by itself does not tell us which one of these is a limiting reactant. We have to take this number and divide it by the coefficient in the balanced chemical equation. So that's what we refer to as R when we were doing stoichiometry problems before. So we divide the number of moles of phosphine, pH3, divided by its coefficient. The coefficient for pH3 is 2, so that's the number that goes there, and this comes out to 0.38. And then for O2, the number of moles is 0.914. So there are more moles of O2, but the coefficient in the balanced equation is 4. And so when we divide the two, we get a number that's smaller, 0.23. So this number is smaller, 0.23, so that tells us that O2 is the limiting reactant, which is all this question was asking. Okay, so just like any stoichiometry problem, if we're doing stoichiometry with gases, if we use the ideal gas equation to tell us the number of moles, we can then follow the same steps we learned before to determine which of those is limiting reactant, and there's nothing different about it. Alright, and then finally the last question is how many grams of P2O5 are formed? And so for this we need to know this is one of our products. And so we start with moles of limiting reactant. We found that oxygen was a limiting reactant and that there's 0.914 moles of O2. That's our limiting reactant. And then we want to figure out how much of the P2O5, the diphosphorus pentoxide, is formed. So we see that this has a coefficient of 1, so there's 1 mole of P2O5 formed for every 4 moles of O2 that reacts. So this is just mole ratios, nothing different about it. And then finally we need to use the molar mass to find out the grams of P2O5 that are formed. So this molar mass is 141.94, so that means there's 141.94 grams of P2O5 per 1 mole. So we get 32.4 grams. That's the maximum amount of that solid P2O5 product that can form in this reaction. Alright, so again, gas stoichiometry is mostly just a review of the stoichiometry stuff we already know. It's just using, in some cases, the ideal gas equation to tell us the number of moles, and also recognizing that for ideal gases, number of moles, volume, and pressure are all directly related to each other, so we can also interpret these coefficients as volume ratios and pressure ratios as well, depending on the situation. Now, an older version of these notes that I used last year, we did one more step in this problem, which was to calculate the total pressure at the end of the reaction. Now, I'm not going to do that right here because I realized I was jumping the gun a little bit because we haven't gotten to this part, but that's where we're going to start now. So let's say we wanted to know what's the total pressure at the end of this reaction after we've mixed the gases together, after we've allowed them to react. And the way we would determine that is what we need to know is just the total number of moles of gas. And that's then referred to as Dalton's Law of partial pressures. So let's do a couple of thought questions on this before we introduce the topic in full. Alright, so Dalton's Law says, let's say we have a flask that's filled with 1 atmosphere of nitrogen, N2. You add an additional 1 atmosphere of N2. What would be the total pressure? So A is 1 atmosphere, so the pressure stays the same if we add another 1 atmosphere of N2. B is 2 atmospheres, which would be the sum of the two. C is 0, or D is who cares. Hopefully not many of you say that one. So what do you think the answer would be? So I heard a few people say it. So yeah, the correct answer is B. So we know that pressures are additives. If we take one gas at a certain pressure and we add another amount of that gas at a certain pressure, the sum of those two, what we call partial pressures, would give us the total pressure of the final system. Now let's say we do it with two different gases. Let's say we have 1 atmosphere of N2 and we add in 2 atmospheres of O2. Now let's assume that the two don't react with each other, which they don't under normal conditions. So if we started with 1 atmosphere of nitrogen and we added 2 atmospheres of O2, what would be the final pressure in this case? Is it any different because we have two different gases? So what does anybody think the answer would be here? Alright, so I heard some people say C, so that's good. You didn't overthink this one. So it doesn't matter what the identity of the gases are. As long as they're ideal gases and as long as they're not reacting with each other, the total pressure will just be the sum of all the partial pressures. So what this tells us is that pressures are additive. And the reason for that is that gases mix homogeneously. Okay, because gases, as we said, they fill all available space. So when you mix two together, they're going to completely mix up together and fill up the entire volume of the container that they're in. And then the other thing that's important is that each gas in a mixture behaves as if it were the only gas present. So there's no interaction between the two samples of gases. So if we mix two different samples of gases together, in the second example we did nitrogen with oxygen, the nitrogen doesn't know that there's any oxygen present, and the oxygen doesn't know that there's any nitrogen present. They just behave as if they're the only gas present in the mixture. So we're going to talk in more detail next time about the stipulations or the properties of what makes something an ideal gas versus a non-ideal gas. But one of the properties of ideal gases is that they don't interact with each other at all. When you mix two ideal gases together, they just behave as if they're by themselves, and there's no effect except if we talk about like total pressure. But the individual gases in the mixture behave normally as if the other gas isn't even there. Okay? So that's what leads us then into another gas law, which is referred to as Dalton's Law of partial pressures. All right? So this is John Dalton, also quite angry with having his portrait done, apparently. And so what Dalton's Law of partial pressure deals with is a mixture of two or more gases. All right, so we've talked about scenarios where we have a sample of one gas, and then we're calculating pressure or volume or temperature as that gas changes its state. We talked about chemical reactions involving gases where the two are reacting with each other. Dalton's Law deals with a situation where we have two different gases mixed together, and how does that then relate to then their total pressure and other factors. So as we said, pressures are additive. So if we have a mixture of two or more gases, and we know that the individual pressures of the gases in the mixture, the total pressure is just the pressure of the first gas plus the pressure of the second gas plus the pressure of the third, however many gases we have mixed together. If we know all of their individual pressures, the sum of those will give us the total pressure of the mixture. Now these individual pressures that I'm labeling as PA, PB, PC, the pressures of the gases in the mixture, those are referred to as partial pressures. Okay? So that's what we refer to as partial pressures, where if we know the individual pressures of the gases that are mixed together, the sum of those gives us the total pressure. Now in many cases we don't know the individual pressures of the gases, but there's a relationship we can derive that involves the moles of each gas that are present. So again, using our favorite equation, the ideal gas equation, or at least one of our favorites, hopefully, we can say that the pressure is equal to nRT over V. And so that means we can rewrite this form of Dalton's Law in terms of number of moles. So the total pressure is going to be the pressure of gas A, which is the number of moles of that gas, times RT over V. So all of these gases, when they're mixed together, they have the same temperature and they occupy the same volume. So it's going to be the number of moles of A times RT over V, plus the number of moles of the second gas times RT over V, plus the number of moles of the third gas times RT over V, and so on forever, however many gases we have. So we're just rewriting the sum of the three partial pressures in terms of nRT over V, which is just the rearrangement of the ideal gas equation. And we do that for each of the gases separately. And what this then adds up to is we can factor out RT over V, and it's just the sum of all the moles. So it's the total number of moles times RT over V. So as I've kind of already alluded to, if we know the total number of moles in our sample, regardless of whether it's a mixture of more than one gas or just a single gas, if we know the total number of moles, we can calculate the total pressure using the ideal gas equation. But then what this leads to is perhaps the more useful form of the equation, or the form of the equation we're going to have to use in a lot of the problems we do, which is in terms of what's called mole fraction. So the pressure of gas A is going to be equal to the mole fraction of that gas, chi. So this is another Greek letter to add to our Greek alphabet that we're slowly learning. And we multiply that by the total pressure. So if we know these two terms, the total pressure in the mixture and the mole fraction of A, we can calculate the pressure of A. Now what is mole fraction? So this term chi here is the number of moles of A that we have, the number of moles of that gas, divided by the total that are present in the mixture. And so this, as I said, is referred to as mole fraction. There are some other equations that you'll learn next semester in Chem 2 if you take it, that also use mole fractions. So this is a useful quantity in some areas of chemistry, and this is the first place we've seen it. A mole fraction is just when you have a mixture of gases or a mixture of anything really, it's the number of moles of that substance divided by the total number of moles that you have in that mixture. And so then this allows us to calculate the partial pressure if we know the mole fraction and we know the total pressure. Now to hopefully prove that this is true, if you can accept the fact that the total pressure is equal to PA plus PB plus PC for three gases, let's say, where again these are the partial pressures. If you accept that that's true, we can rewrite these in terms of mole fraction. So the pressure of A is going to be its mole fraction times the total pressure. Pressure of B is going to be its mole fraction times the total. Pressure of C is this mole fraction times the total. And so if we factor out, we get the sum of the mole fractions, chi A plus chi B plus chi C, times total pressure. And if the sum of all of the mole fractions will have to be equal to 1, because in any mixture, the sum of the fractions of the mixture equals 1, and so this would just be equal to 1 times total pressure. So this is kind of a roundabout way of hopefully convincing you that this relationship works, but this is the form of Dalton's Law that we're going to use most often. The partial pressure of a gas in a mixture is equal to its mole fraction times the total pressure. If we add all of those up, the sum of the mole fractions is 1, and that gives us then that total pressure when they're all summed together. So a few different ways of thinking about the same concept, but it again relates to the idea that the sum of the partial pressures of a gas give you the total pressure, and when gases are mixed together, that's how they behave. Alright, so let's do a quick problem with Dalton's Law. So let's say we have a mixture of two gases, 40 grams of O2 and 40 grams of helium at a total pressure of 0.9 atmospheres. We want to know what is the partial pressure of O2. So what those last relationships told us is that partial pressure depends on the number of moles of each gas, not on the masses. So the masses here, we can't use these directly, but we can use those to find number of moles. So again, we're looking for partial pressure of O2, and the relationship we just learned is that that's going to be equal to the mole fraction of O2 times the total pressure. And so we just need these two terms to tell us what the partial pressure of O2 is going to be. We see that the total pressure is already given to us at 0.9 atmospheres. So we know the total pressure, we just need to find what's the mole fraction of O2. And again, mole fraction is going to be the number of moles of that gas we have divided by the total number of moles. In this mixture, there's only two gases, so that's going to be the number of moles of O2 divided by the number of moles of O2 plus the number of moles of helium that we have. Okay, so the total number of moles is just the sum of whatever gases you have in your mixture. In this case, there's only 2 of them. Alright, so we have to find the moles of each gas. This should be old hat by now. So we have the masses of each. We convert them to moles using molar mass. So we have 40 grams of O2. The molar mass of O2 is 32. So we divide by the molar mass to get moles of O2. So our mixture has 1.25 moles of O2. And then for helium, if we go to the periodic table, we also have, in this case, 40 grams of helium. And the atomic mass of helium is 4. So there's going to be 1 mole of helium per 4 grams of helium. And that's going to give us then 10 moles of helium. Alright, so those are the 2 molar amounts. And so when we calculate mole fraction, we get 1.25 moles in the numerator. That's the moles of O2. In the denominator, we get the sum of the 2. 1.25 moles of O2 plus 10 moles of helium. So that comes out to 0.111. So the mole fraction of O2 in this is 0.111, or alternatively you can interpret that as 11% of the mixture is O2 in terms of moles. And so then we just multiply that mole fraction, 0.111, times the total pressure, which is 0.9 atmospheres, .09999 atmospheres. So only a relatively small fraction of that total pressure comes from O2. So even though the 2 gases are present in equal mass amounts, it's the relative number of moles that dictates which one has the higher or lower partial pressure. And so in this case, we have much fewer number of moles of oxygen compared to helium, so the partial pressure of oxygen will be much lower. Now to get the partial pressure of helium, we would just subtract this number from the total pressure, 0.9. Or alternatively, just do this calculation again for helium. So the sum of the 2 pressures has to equal 0.9. If we know the first one, we can just subtract it from that to get the second one. So that's not asked here, but that's how we would do that. All right, so any questions on that application of Dalton's Law? All right, so that's a relatively straightforward problem involving Dalton's Law. Now the next thing, the other thing we can do with this is, and this is just one of those types of problems that general chemistry textbooks love for whatever reason. I think they're kind of cool too, but whether you think this is practical or not is, I guess, in the eye of the beholder. So it's an application of Dalton's Law that allows us to do some things with gas stoichiometry. So first, let's describe the experiment that's going to be, or simulated at least when we do these types of problems. So what we have here is some reaction mixture, which is usually solids, or it could be something that's not gas phase, basically. So either a solution or it's 2 solids mixed together, whatever the case is. So I'm going to label that as number 1. So this part over here on the left side is going to be whatever chemical reaction we're doing, which is going to not involve gases itself. It's going to be either a liquid phase reaction or a solid phase reaction, but it's a reaction that produces a gas. So this type of apparatus that I'm going to describe here, which relies on Dalton's Law of partial pressure to understand the results, this type of apparatus is going to be used for studying reactions that produce a gas as a product. So you're doing the reaction over here on the left side. As we're showing here, you often heat up the reaction to get it to go. And then what happens is throughout this entire apparatus, so this tube here that's in the middle, which I'll label as number 2, the gas gets transported to the other side. So it gets transported to the collector. And then once it goes into the collector, it gets bubbled through water. So you have an inverted jar of water, an inverted container of water. The gas bubbles through there, and then it collects in the headspace of the container here. So I'm going to label that as number 3. So this number 3 that I'm labeling is going to be where the gas is collected, and it displaces the water that's present in the inverted container. Alright, so what we do here then is we collect the gas up here in the headspace, and by measuring the amount that volume changes of the liquid or of the gas that's above the liquid, however we measure it, that volume change is going to tell us then what volume of gas was produced by this reaction. So we're displacing water, we're measuring the volume change of the water, and that tells us then how much gas is produced. Now the thing that we have to keep in mind when we do this is that the gas that's up here in the headspace of our container, whatever gas we're collecting, it's going to be that gas, plus there's also going to be some gas phase water molecules. So this is something that we'll deal with in more detail in Chapter 9, but what we have to be aware of for now is that there's going to be a vapor pressure, as is called, for water. So when you collect a gas over water, as we're doing here, we're collecting the gas in an inverted container of water, the pressure the total pressure of the system, which would be atmospheric pressure in this case if it's open to the atmosphere, that total pressure is going to be a sum of the pressure of the gas you're collecting plus the pressure of the water vapor that's above the sample of water. So when you have a sample of liquid water, even though the vast majority of the molecules are in the liquid phase, a small portion of those escape into the gas phase, even at room temperature, and so you get a small pressure above that sample that we refer to as vapor pressure. So as I said, we'll deal with more details of vapor pressure next time, but what you need to be aware of for now is that some water molecules escape into the gas phase, so they escape the surface of the liquid, and they create a small partial pressure above the liquid. Give this a second to recover. All right. And this partial pressure is a constant, but it is temperature dependent. So depending on what temperature you're collecting the gas at, you're going to have a different partial pressure of water that contributes to the total pressure of your system. Now, why that's important is because what we're going to be doing here is we're collecting a volume of gas that we're measuring using this apparatus. We're going to use PV equals nRC to tell us how many moles of gas that is, but we have to be aware of the fact that the total pressure of the system is the sum of the pressure of the gas and the pressure of the water. So the pressure that we put into the ideal gas equation has to be corrected for the partial pressure of water. So the best way to understand this is just to do some example problems. So let's say we did this reaction here. So we add calcium carbide, which has the formula CaC2, and if we add that to water, it produces a gas called acetylene, which, if any of you are welders, you've probably used acetylene before. And so you add calcium carbide to water, and it reacts in this way to form C2H2, which is a gas, and then aqueous calcium hydroxide, which stays behind. So we're collecting a sample of acetylene over water at 23 degrees Celsius, and we know that the total pressure is 738 torr. So again, typically when we're doing these experiments, we're doing them at atmospheric pressure. So if we know the room pressure using a barometer, that's going to be the total pressure of the system. And we know that the volume of gas that we collect is 523 milliliters. If the vapor pressure of water is 21 torr at this temperature, how many grams of acetylene are produced? Alright, so there's a lot going on here, but the way we approach these problems is to recognize first that the total pressure of our system is equal to the pressure of whatever gas we're collecting, C2H2 in this case, plus the vapor pressure of water, which I'll abbreviate as PH2O. So if we want to find what the partial pressure of the product gas is, C2H2, the partial pressure of that, we just have to subtract it from the total pressure. So the pressure of C2H2 is the total pressure minus the vapor pressure of water. So it's a small correction we have to do to get accurately what the pressure of this gas is. So in this problem, we have 738 torr as our total pressure, and we're told that the vapor pressure of water is 21 torr at this temperature. Now, you're never going to have to memorize the vapor pressure of water, or you're never going to have to calculate it from first principles, so that'll be given to you in the problem, but we have to account for it and make sure we don't forget it. The most common mistake people make in these problems is to forget to make this correction. And so when we do that, the actual pressure then of the gas is only 717 torr. Now it's not a huge correction as you see, because the vapor pressure of water is pretty low at room temperature. It's only 21 torr in this case. But if you forget to do this step, you'll get an answer that's slightly off from the correct answer. And because we're cruel in this way, we'll set out the problems in such a way that if you don't make this correction, you will get the problem wrong. So that's the reality. Okay, so this is the actual pressure of the gas, C2H2, that we're collecting. And then what we're going to do once we have its pressure is we're going to use the ideal gas equation to find the number of moles. And then in this problem, it's asking us how many grams that corresponds to. So once we have a number of moles, we can convert that back into the grams. So the first step is to get the pressure. Once you have the pressure, it's just using ideal gas equation in ways that we've already done today. So if we want to find the number of moles of C2H2, it's going to be pressure times volume divided by RT. And so what we have then is we need to have the pressure, though, needs to be in atmospheres because we're using the value of R. So we do have to do some conversions very often from torr to atmospheres. So if we have 717 torr as our partial pressure of acetylene, we have to convert that into atmospheres by dividing by 760. So that's 0.943 atmospheres. So that's our pressure. We're told in this problem that we collected 523 milliliters. That's the volume of the gas. That's the volume the gas occupies. That needs to be converted to liters. So we have 0.523 liters of gas. Then we divide that by RT. R is the familiar universal gas constant, which you'll not have to memorize. It's on your periodic table. And then the temperature of the system is 23 degrees Celsius, which needs to be converted to Kelvin, 296. So we add 273 to that to get it into Kelvin. And so I can, let's see, make sure I can read my own writing. 0.0203 should be the number that you get. Alright, so that's the number of moles of acetylene. And then since these problems are pretty labor intensive, I have a little bit more space for work here. So the last step is to convert that into the grams. Okay? So let's try to keep as much of that as we can so you can still see it if you're working on it. And then the mass of C2H2 is just going to be the number of moles that we found and the molar mass, which I think we gave you in this problem, is 26.04. Yes, 26.04 is the molar mass, so that's given to you. I think I did that wrong because I'm trying to talk and write at the same time, which is a bad mistake. Alright, 26.04 grams of C2H2 per mole, so we have to put that in the top, of course. And that comes out to 0.529 grams, I think. So that's the mass of that product that we would collect in this apparatus. Okay, so this is a typical type of problem you'll do. You're going to have to remember, again, to subtract the vapor pressure of water to get the partial pressure of the gas. Use the ideal gas equation to find usually the number of moles, and then from there it becomes like any other stoichiometry problem. So once we have moles of the product, there's other things we can do with this. So here we took the number of moles of product and converted it into grams, which may or may not be a useful quantity depending on the situation. But let's say we wanted to know, if we get 100% yield, how many grams of the calcium carbide, which has this molar mass, were required to produce the acetylene gas. So this becomes then a stoichiometry problem where we're looking for the mass of the reactant that we use. And we know from all the work that we did in the previous step that we formed 0.0203 moles of our product, C2H2. And if we want to find out how many or how much of our reactant we needed to produce that, it just becomes a simple stoichiometry problem where we use, again, mole ratios. So there's a coefficient of 1 in front of CaC2, calcium carbide. Also a coefficient of 1 in front of this product, so it's a 1-to-1 mole ratio. So that determines how many, so we need that many moles of calcium carbide, and then to convert that back into a mass, we use its molar mass, which is 64.1. And so we get is 1.30 grams. So if we put 1.30 grams of calcium carbide in water and we allowed the gas to escape and we collected that gas, it would displace 521 milliliters. We worked backwards in this case to use that information to determine the number of moles. So we got done a little bit early today, which is great because it's bonus quiz time. So take a moment to get your quiz forms out. Alright, and if you don't have a quiz form, make a friend quickly. Alright, same story as before. This is more of a conceptual question, I suppose, so I'll give you 2 minutes to do it. There should be plenty of time to think it through. And then once you're done, you can pass your quizzes to the aisle. I guess we've done a little bit early today, so I could stay for like 5 minutes if anybody has any questions that you were dying to ask me at the end of class. I said I had to leave early, but I can stay for a little bit longer. But anyway,